Hey guys, let's go ahead and take a look at a couple of problems here in Achieve section 4.1. Um, the first one here that I want to look at with you is number 2, and it is a bit tricky because it doesn't explicitly list to you what the a and the delta x is in the problem, but we need to be able to pull that out of what they ask in the problem. So notice here, they say that we have a function f of x that's equal to, in my case, 11 over 1 plus x squared. They're asking what the change in the function is between 3 and 3.2. So they ask you to evaluate the function at 3.2 minus the function evaluated at 3. So if I'm trying to find that change in the y values, y2 minus y1, remember, a is just the first value of x of interest. Well, in this case, clearly, that's x equals 3. We're trying to find the change in y as x goes from 3 to 3.2. So the first value of x of interest we call a. A in this problem is 3. Delta x is just the change between the x values. So you'd say, well, the change in the x values that's going up 0.2, so delta x is 0.2. So now I can say my approximation function, which is f prime of a times delta x, in this case, it's just going to be f prime of 3 times 0.2. So whatever the slope is at 3 times the change in x, 0.2, should approximate the change in the y values from 3 to 3.2. So in order to get to that, I have to have the derivative. I took my function 11 over 1 plus x squared, took the derivative of it, we squared the denominator, brought the denominator to the numerator times the derivative of the numerator, but derivative of any constant is 0, minus the numerator 11 times the derivative of the denominator, and derivative of x squared gave me 2x. So this easily simplified to negative 22x over 1 plus x squared quantity squared. So now the change in the function's values is approximately equal to the derivative evaluated at 3. I plugged a 3 into this derivative, negative 22 times 3 over 1 plus 3 squared quantity squared. That gave me a negative 66 in the numerator and a 10 squared in the denominator for 100. I took that negative 66 over 100 times 0.2, and I have that the approximate change in this function's values as x moves from 3 to 3.2 is negative 0.132. So clearly, it should be moving down. I'll go ahead and enter that in. Delta f is approximately equal to, this is where they should want the negative 0.132. Now I move on and to go to the next step in this problem, it's wanting to know what the actual change is. Well, the actual change, that's just when you plug 3.2 and plug 3 into the original function. So notice I say the actual change of my function delta f is nothing more than f evaluated at 3.2 minus f evaluated at 3. And I did that on the calculator here. I just said, well, f evaluated at 3.2, that's going to be 11 over 1 plus 3.2 squared minus the function evaluated at 3 is going to be 11 over 1 plus 3 squared. And Achieve is wanting the answer to 6 decimal places, so I said negative 0.121352 there. So I pull that answer out. I'll go ahead and put that into Achieve here. We have the negative 0.121352. Now, the next portion of the problem is wanting you to wanting you to compute the error and the percentage error. It's wanting the error to 6 decimal places. So you'll see here where I did that, I said, well, the error every single time, it's nothing more than the absolute value of the difference between the true value and your approximated value. So that's going to be negative 0.121352 minus a negative 0.132. And when I did that on the calculator, 6 decimal places, I had the 0.010648. Then I'll go ahead and talk about this. The percentage error is nothing more than the absolute value of that error divided by the true actual value of the change in the function, which is right here. Now notice, you would just take the error that you got. You don't divide by negative because you know the absolute value is going to have to take the positive of the sign anyway. So I think what I would do here is just say 0.010648 divided by 0.121352. We'll get that decimal value times 100 to get the percentage, and you can see that there's a percentage error of 8.77%, and it wanted 2 decimal places on the percent in this problem. So now all I have to do is go back into the problem, enter in that information needed. The error in the linear approximation, that was the answer we came to at the 0.010648. And then the percentage error of our approximation was the 8.77. And notice they already have the percent sign there at the end. So we should just be able to go up here, check the answer, and it says correct. Now, for the next one here, the linearization of this function, the function I have is 6x cubed, and I'm trying to evaluate it at the particular value of x equals a, which is 1. So what I was trying to discuss in our notes for this section is that the linearization formula, it's really nothing more than the slope of the tangent line at the point of interest. Our formula for the linearization formula is all you're going to have to do is evaluate f at the point of interest plus f, the derivative of f at the point of interest, times x minus a. Well, the point of interest in this, I need a line of this function that approximates the function best when x is equal to a, which is equal to 1. So you say, well, all I have to do then, my linearization function should be f of 1 plus the derivative evaluated at 1 times x minus 1. So then it becomes an easy problem. First of all, you just have to tell me what f of 1 is. You plug a 1 into your function, 6 times 1 cubed, I get the 6. You take your derivative, and you say, well, that's just going to be 18x squared. Evaluate your derivative at 1. It's going to be 18 times 1 squared is 18. Thus, our linearization function should be f of 1, 6, plus the derivative evaluated at 1, 18 times x minus 1. This should be the answer. Let's see if it plugs in. We have 6 plus 18 times the group x minus 1. X minus 1 should be perfect. I'll check that answer and you'll see absolutely. Okay, guys, I hope this helped you out with these questions here in section 4.1. If you have any other questions, please let me know.